Okay, so I'm eventually going to lead up to this these things called the McDonald eta function identities, but along the way, well, at least for a start, maybe I want to pick up the thread from where Raghavan left off in terms of talking about the affine Weyl group itself. So just make a few more remarks about the affine Weyl group and its action on that space H star. And then I sort of want to kind of take a massive flashback and just talk about some of the history, the context, the motivations for these identities, where they came from, their precursors and so on. And maybe along the way, the next two lectures will sort of be dedicated to looking at the various ingredients in the proof. But let me begin with the affine Weyl group. The Weyl group of an affine Kac-Moody algebra, and I am just going to simplify my life a little bit. So recall this morning that the basic ingredients are, so we start with some finite dimensional simple D algebra, so let's call it G with a dot on top. This is some complex simple finite dimensional D algebra, and of course it's got a Cartan subalgebra which we will denote H with a dot on top. So H dot is or H naught, G naught. So this is a Cartan subalgebra of G, and then we performed this loop algebra construction which produced the affine Kac-Moody algebra associated to G dot. So that's well, what we call L hat of G, L hat of G dot. So will be first obtained by forming this Lie algebra, then performing a central extension then adjoining a further degree derivation. So we put all these things together, then we had the formula for the bracket, and that was the affine Kac-Moody algebra L hat of G dot. So let's call this G for now. I'm sorry, what? K is the central element. So sort of this is the Lie algebra which has a natural bracket, and then you sort of need to throw in an extra element in the center, that's the K. There's a formula for a cocycle which defines this central extension. So when you take a commutator of two things from here, you incur a coefficient of K, and the precise coefficient is given by that cocycle formula. Okay. Okay, and then we define sort of by fiat the Cartan subalgebra of this resulting affine Kac-Moody algebra as take the finite dimensional Cartan, and then you add these two extra elements. K and T, and then there's all the same kinds of things that happen to the finite dimensional setup happen here. G has a weight or a root space decomposition. It's called the set of roots as delta, and as mentioned, the set of roots sort of splits into two categories. You talk about things called real roots and things called imaginary roots. Okay, and the okay, so I guess I'm at the moment going to worry about the Weyl group, but okay, before that, so what are these sets. She also mentioned what these things are, right, in this setup. So, for example, the real roots, so maybe it's a good time to recall this, the set of real roots which we will call delta real, recall was just the following. So observe, these are all subset of H star, and so we first think of H0 star, as Raghavan mentioned this morning, as sitting inside H star. So observe, you can think of H0 star as a subset of H star by just extending it as 0 on K and D. So this is the usual extension. So if you have any element lambda here, you map it to the same lambda extended by taking the value 0 on these two elements K and D, which lie outside, these two extra basis elements. Okay, so that was the extension, and we in fact also had a basis for H star which was dual in some sense to this basis. So we think of H0 star, things which come from functionals here, and then elements which are now 0 on H0, but 1 on K and 0 on D, or 0 on K and 1 on D, right. So we take these two extra elements which we called, so the one dual to K is called lambda naught, the one dual to D was called delta, right. So this is the structure of H star, and so if your H naught was a L dimensional vector space, so if this was L dimensional, we have sort of added this extra 2-dimensional space. So you have an L plus 2-dimensional vector space, and so the real roots, for example, are elements in this L plus 2-dimensional vector space which have the following form. They look like, so maybe we should call, so let me just give this a name beta. I will use alpha to denote things which come from H naught. So they are the form alpha plus n delta, where alpha is a root of the underlying finite. So therefore it's an element of H naught star, and n can be any integer. Okay. So for every root alpha of the underlying finite dimensional Lie algebra, you look at all things of the form alpha plus n delta. So you translate it by all integer multiples of delta, and those are all the real roots, and the imaginary roots are much simpler. In this case, they turn out just to be n delta. Here now n can be any integer except 0. Okay. And in fact, from the explicit construction of this Lie algebra in terms of these, in terms of the loop algebra and so on, one can further say what these root spaces consist of. For example, the root space alpha plus n delta, so we had this, if we take the root space alpha plus n delta, what are these elements? Well, they are just elements which come from G naught alpha and then you sort of tag along the nth power of t. Okay. So it's sort of that copy of G naught alpha is sort of sitting at the nth level. That's the root space corresponding to alpha n plus n, alpha plus n delta, and the n deltas are these root spaces. Okay. So when you actually, yeah. No. So G, yes, thank you. Yes, indeed. Thanks. So G n delta is H naught, which is the 0 root space of G naught, and so you're thinking of n delta as 0 plus n delta. So it's really the same prescription as above, except where instead of alpha, when you put a 0, the eigenspace is now the Cartan subalgebra. So it's the same prescription in some sense. So this decomposition here, if you sort of see, it splits further into these various pieces, and these are in fact the various root spaces corresponding to these guys, right. So just sort of a review of this construction of the affines and what the roots ended up being and so on. But now of course we are interested in the Weyl group, which we define. So it can sort of be defined, so this is what I'll call the affine Weyl group. You can think of it, so as in the finite dimensional setup, you're going to think of it as, it's defined naturally as a subgroup of GL of H star, which is generated by, so if you remember in the finite dimensional setup, it was generated by the reflections S alpha for all roots. So here the definition of the Weyl group. You could think of it as follows. You either say it's generated by, so it's a group, subgroup of GLH star generated by S alpha, where alpha, well, to sort of copy the finite dimensional setup, you would have to say overall roots, right. So for example, I should let it run over everything of the form alpha plus n delta as well as everything of the form n delta, right. So if one were to just mimic the finite dimensional definition of the Weyl group. So now firstly we need to make sense out of all these things. For example, what does it mean to talk about the reflection S alpha? Okay. In the finite dimensional setup, we had one of two ways of doing it. So Raghavan sort of mentioned one of them this morning, which is you sort of look at the formula for a reflection. So firstly I need to make sense out of these guys. Again, I want to call these betas rather than. So the question now really is, what do we mean by this reflection S beta? So what element of GL H star is it? Okay. So we need to say how it acts on these elements of H star, where beta is now going to be either a real root or an imaginary root. And the answer is, of course, you could do the following. Sort of here are the two candidate choices. You could say, well, let's define it as follows. S beta after all had a formula, right. So here's the definition. It's lambda minus lambda beta check beta, right. So this was the formula which worked for reflection in the finite dimensional setup, and we could try and mimic the same thing. So let's define the reflection as beta, where beta is now an element of, say, it's any of the roots, by saying S beta of lambda has to be defined by this formula. Okay. Except now the trouble is, what is beta check? In the finite dimensional setup, beta check was the co-root. It was actually an element of H, right. This should now technically live in H. If one could make sense out of this, then of course, in the finite dimensional setup, it had these nice properties. Beta evaluated at beta check was 2. Well, I guess that was more or less the only property, right? Beta evaluated at beta check was 2. So you need to sort of look for some nice elements, checks in this setup. Okay, and of course, one way around this whole business is to just say you will not take all elements of delta, but only these so-called simple roots. Okay. So remember, in the finite dimensional setup, the Weyl group was also equivalently defined as the group generated by only the simple reflections. Now that is something we can continue to do here. We could say instead of all beta in delta, let's only take the simple betas, right, where the simple ones would be alpha 0 through alpha L, right. So Raghavan also defined what alpha 0 was. So you would only take those and define that to be the Weyl group. And there, of course, there is also a natural pairing notion of what alpha 0 check means, alpha 1 check means. There are some canonical choices for those. That's one thing you could do. We could sort of make this work along those lines too. I should at least modify my definition a little bit. So one of the possible definitions of the Weyl group is actually this. Okay. So we can't quite define the Weyl group as the group generated by all reflections over all roots, because the imaginary roots cause problems. And if you sort of see what kind of problem they would cause, that will sort of become apparent in just a little while longer. But for now, let's take this as the definition. It's the group generated by all the real roots or equivalently by just the simple roots. So let me say this is the definition, and the equivalence of these two things I'm just stating for now, I'm not going to prove it. So this is just over all S alpha i's okay. So the affine Weyl group is defined by one of these two equations, and why these two equations are the same I'm not really saying much about. Okay, but I'm sort of for now I want to, for the computation I'm going to perform, let me now take the other point of view. There was another equivalent formulation of this in the finite dimensional setup using the form, right? We could convert, using that invariant form, we could convert things in H into things in H star, where you now have to evaluate the form. So remember we had this formula for a reflection, 2 lambda beta okay. The finite dimensional setup, this would be what the reflection is, where this form was just, so where for a finite dimensional setup where, so here I should say in the finite dimensional case, that form was chosen to be some non-degenerate Weyl group invariant form on the dual of the finite dimensional Carnot subalgebra, right? Okay, so now let's try and use this as our definition of a reflection in the affine case. Okay, so I'm trying to make sense out of what these reflections mean, and to do this I will just use a form. Okay, and so that's going to be the normalized invariant form. So the form now let's define, so let's assume that we start with something be let's say W0, for example the killing form. So maybe we'll just say be the killing form, okay, maybe, I mean I want to normalize it as well, so let this be non-degenerate W0 invariant form on H0 star. So at the moment I'm only focusing on the finite portion. For example, the killing form, example of multiple of the killing form. So I'm already tying myself up into tangles. W0 invariant, so I should probably worry a little bit about what I mean by W0 then, right? I mean thinking of it in terms of, okay, I guess it makes sense if for the moment I pretend I don't have my affine Lie algebra at all. I just have G0, my finite dimensional Lie algebra, and there of course I have some form on H0 star, right, where I know what W0 means and so on. Okay, great. So for the moment I only have a finite dimensional Lie algebra in which I can do all these things. And now I want to extend this form to the whole thing. So let's extend this form to H star, all of H star, by the following prescriptions. We say that H0 star is prescription number 1 says that you think of this as an orthogonal direct sum, meaning to say H0 star under the form, when you extend it, I'm sort of thinking of it as it's perpendicular. So this part and that part are mutually orthogonal under the form. Okay, that's the first description of the form. Now the only thing that remains to be said, so on H0 star I know how the form is, it's just the usual form. I'm now trying to extend the definition, and now I'm saying this and the other part are mutually perpendicular. So I only need to tell you what the form is on this second component, what it does to K and D, except I'm right. k and d are not in H0 star, they are not in H star, this should be lambda naught and delta. Right. So, we define the inner product or this form on lambda naught and delta by saying lambda naught and delta are isotropic elements and their inner product is 1 and the form. Okay, in other words, if you think of a form as really being sort of like a matrix, it says, you know, you have an L dimensional, you have these L basis vectors which correspond to H0 star. There you have whatever matrix you already have. It's just a matrix of the original form. Matrix, which looks like that. So when you construct the matrix of this, the extended form is, you do it as follows. With respect to this basis, it's just this 2 cross 2 matrix with ones on. So you extend the form this way. The first thing to notice is that this new definition, this new form that one has on H star is non-degenerate, because the determinant of this overall matrix would be, you know, just a blocks, 2 blocks. This guy was positive definite form to start with, so it's certainly a non-zero determinant, and this determinant is -1. So it's a, you know, firstly it's a non-degenerate form, sort of on the real span of, you know, H0, well, on the real span of these guys and on lambda naught and delta, you will see it has signature, you know, all pluses and 1 minus. Okay. So anyway, that's sort of just something on the side, but I want to use this form to define my Weyl group elements. So you take this form, and let's also assume it's normalized such that theta theta is 2. Okay, so let's assume further, assume it's normalized like this, where again theta is the highest root of the finite dimensional guy. And maybe to in fact even simplify matters some more, for now let's just pretend that G0 is, you know, one of these what we call simply laced Dynkin diagrams. For example, think of G0 as just being the Lie algebra SLN, for example. So what I'm saying is, for the moment, think of it as one of these 3 series of Dynkin diagrams, AL, DL or E6 using that form by just applying this formula. It's 2 lambda alpha I that will be my definition of these reflections. So now my question is really this: accept for the moment that, you know, I have this form which is, you know, this will turn out to be the same as the normalized invariant form that Punitha defined, and my Weyl group is just these the set of the group generated by all reflections S alpha i's which are given by this formula with respect to that form. Right. So now if you take all this for granted, then question is, what can I say about the structure of this group? Right. I have defined the form. Once I have the form, I know what S alpha I does to every element. Right. So it's now sort of a linear algebra problem. I gave you a form. I'm telling you it's a certain all these transformations, these operators on that vector space, they generate some group, and the question is, what can one say about that group? So the first thing to observe is this makes sense because the alpha I which appears on the denominator is not 0. Right? This reflection would only make sense if your root had length which is not 0, and that's the reason why when I sort of defined this, I said I want to restrict beta to be only a real root, because imaginary roots were precisely those which are multiples of delta, and the normalized invariant form has the property that delta delta is 0. Okay, so delta is an isotropic vector, and so you couldn't possibly define a reflection with respect to a vector of norm 0. Okay. So notice, like Raghavan mentioned this morning, it's not a positive definite form, right? It's just some non-degenerate form, and so you could very well have vectors of norm 0. So you should be a little careful while working with these. So I cannot really allow delta as part of my definition, so I only restrict to the real roots and say it's the group generated by those, which will turn out to be equivalent to the group generated by the simple reflections. Okay, so let's see. Firstly, alpha i's are all non-zero. In fact, they're all 2. Okay, so under my simplifying assumption, observe alpha i's are all the simple roots. This would in fact be the same as theta theta. All I from 1 through n. Right? So here I'm always going to assume this now. All roots have the same length for the finite dimensional Lie algebra. So the alpha i's are all roots of the finite dimensional Lie algebra, therefore they all have length 2. But the question is, what about alpha 0? Right? Alpha 0 was not a root of the finite dimensional Lie algebra, it was this extra root that we added. So recall, alpha 0 was defined as delta minus theta. Right. So alpha 0 is not an element of H0 star, it has a component along delta. It has an extra component along delta, right? But I claim, it's still 2, because let's compute alpha 0 itself, it's delta minus theta itself, right? So why is that 2? Because delta with theta is 0, right? Because delta and these two parts are orthogonal. Delta with anything here is 0, but delta with itself is also 0, right? So this is the same as theta theta, so it's also a 2. Okay, so it turns out that even alpha 0 is a root of length 2, and so this reflection now makes sense for every one of the roots. And in fact, I can now simplify my life a little bit, because the 2's will sort of go away. So now my reflections look like observe S alpha I, therefore just lambda minus lambda alpha I, okay, because I'm just cancelling the 2 on the top with the bottom. So it just makes it slightly simpler to work with. That's now for all I including 0. And remember, I'm now thinking of it as acting on the entire space H star. Okay. Okay, so back to the same question. What can one say about the group generated by all these S alpha i's? So the first observation, here are the various observations. So the first observation Raghavan mentioned this morning was, you can just look at the subgroup generated by only the simple reflections from 1 through L, ignoring the alpha naught, and ask, what can you say about that group? How does it act on H star? Okay. So the first question is, what do these simple reflections, so here's this formula for the simple reflection. So what do these simple reflections for I greater than or equal to 1, what do they do to delta and lambda naught? Fixed, right? Because you just apply the formula, right? I gave you the form, we have a prescription. So alpha I with delta is 0, alpha I with lambda naught is 0. So they just fix these two extra components, these two extra dimensions, and they only act on the H0 star portion. So, observe that if you look at S alpha i's and you restrict it, so the remaining part, it just acts as identity. So, when you restrict it to, it really only acts non-trivially on the H0 star portion, and there it is just the usual S alpha I, meaning to say for the finite Weyl group, if you for the moment forgot all about the affine construction and so on, you just lived inside G naught, then how would you have defined these reflections S alpha I? Well, you would have said use this formula and apply it where this guy is the form that I have on H naught star, and where lambdas should only be elements from H naught star, right. So, after all you are extending the form, therefore, the formula for the reflection is just, you are just generalizing the formula. So, when you restrict back to H0 star, you get back the same linear transformation. So, when you restrict it down, this would be the same S alpha I, as an element, as defined as an element of the finite Weyl group, okay, as an element of, okay, great, thanks. The Weyl group of G naught thought of as, it's physically the same thing. I forget isomorphism in some sense. Once you restrict, it's physically the same thing. So, therefore, W naught, so therefore, this is now just a, it's isomorphic to the Weyl group of the underlying finite dimensional Lie algebra, because you just take the usual Weyl group action on H0 star, you extend it by identity on the remaining two components, right. So, it's just sort of a trivial extension. So, what you do get, therefore, first observation, the subgroup which is generated only by these S alpha i's for I from 1 to L is just sort of a silly copy of the Weyl group of G naught, right. The actions on H0 star are same, this just has extra identity action on the remaining two dimensions. So, it's physically the same object. But now what is interesting is this extra simple reflection which generates this group. So, we have one other simple reflection. So, we have gotten the finite Weyl group as a subgroup, and now we want to somehow incorporate this extra simple reflection and see how this fits with this finite Weyl group. And to do that, we need to do the computation that Raghavan did this morning. So, now S alpha naught S theta, right. So, this is the object we computed this morning, and there Raghavan showed that when you restrict it to that space P, a certain affine hyperplane, this just acted like translation by theta. It just took lambda and made it lambda plus theta. Okay. But now I want to think of this as a linear transformation on the full space. So, not just on P. So, my goal now is to figure out how this acts on the entire space H0 star. So, observe, after all, this is supposed to be acting on the full space H star, and what I want to do is just write out explicitly the formula for that action. So, let us just calculate, so this is just a nice computation. So, let us compute S alpha naught S theta acting on any element lambda of H star. So, now I am going to take any element of H star and try and calculate this by just applying my formula, that is it. So, I have the formula which is sort of boxed on that far board. So, let me just apply that formula sequentially one after the other and see what it gives me. So, let us apply S theta first. So, my goal is really to compute this. Okay. So, let us apply the first reflection S theta. So, that is still in the finite while group part. Now, the interesting stuff happens when you hit it further with an S alpha naught. Let us start with S theta. So, observe step 1, I compute S theta of lambda. It's just that. It's lambda minus lambda theta times theta. Okay. So, now I need to hit it with the S alpha naught. Okay. So, let me do something further. So, I remember I now want to hit it with an S alpha naught, and so I will convert. So, I will keep going between theta and alpha naught according to convenience. So, again remember the relation between these two things is what is written there. Alpha naught is delta minus theta. So, I will replace theta here by a delta minus alpha naught. Okay, I want to bring an alpha naught into play, so that further action of S alpha naught is very easy on alpha naught itself. So, let me rewrite this as lambda minus lambda theta times delta minus alpha naught. So, it is times delta, then there is a plus, okay. So, I have just rewritten this, and now I will act S alpha naught on this. So, step 2 is to act S alpha naught. So, S alpha naught S theta lambda becomes S alpha naught of lambda. Now, minus some scalar times S alpha naught of delta, right. So, one needs to figure out how an element, the simple reflection S alpha naught, acts on this element delta, right. Now, again we just look at the formula here. S alpha naught delta would be delta, well, for alpha i's we already know the answer, it is just delta again. But for alpha naught, observe delta with alpha naught is what I would need to compute here, right. But delta with alpha naught equals what? What is inner product of delta with alpha naught? I mean, whatever. 0, you would first have to convert alpha naught as delta minus theta. So, it is just delta with delta minus theta, but both those terms are 0, delta delta is 0, delta theta is 0. So, it turns out that in fact delta alpha naught is 0, right. So, in fact S alpha naught acts trivially on delta as well. So, in fact delta is fixed by every single element of the while group, okay, not only by the S alpha i's for I greater than or equal to 1, it is also fixed by S alpha naught. So, every element of the while group fixes that element delta. Okay, so, S alpha naught of lambda minus, so delta is fixed, so I do not need to worry about that term, I will just get back the same term. And then when S alpha naught acts on alpha naught, it gives me minus alpha naught, okay. So, it gives me minus lambda theta alpha naught. Okay. So, I am done, that is pretty much the end of the calculation, except we want to now recast the final answer in a way that does not involve alpha naught. Okay. So, I now want to prefer theta over alpha naught. I want to convert everything here back in terms of theta, so that I only have thetas and no alpha naughts. So, let us do that. Okay. So, the final answer, okay, I still have not really unraveled the first term, maybe I will do it now. So, this is lambda minus lambda alpha naught, it still has alpha naughts in it, minus lambda theta delta, and this guy is now minus lambda theta alpha naught. So, let me keep it for now that way. Now, I will get rid of all the alpha naughts. So, there are several places I need to get rid of the alpha naughts from. There is an alpha naught here, which I will make delta minus theta. Now, there are two alpha naughts here. So, that is a delta minus theta and a delta minus theta, right. So that's basically the computation and one has to do. Replace all the alpha naughts by a delta minus theta, sort of collect all terms together and so on. Okay, so I'm just going to tell you the final answer, right. So it's a computation which can be done, and here's the final answer. It turns out to be lambda plus a lambda delta theta. Okay. For example, that's the kind of term that you would get from here. Right? In fact, that's where it comes from. So you alpha naught becomes a delta minus theta. So there's a delta in here, and then this guy also gives you a delta minus theta. So there's a theta from there. So you pull the delta from here and the theta from there, and you will get that. Okay. Now the remaining things are funky combinations of deltas, thetas, lambdas, and so on. But anyway, here's what it is: lambda plus lambda delta theta. So it's a sort of a nice sort of anti-symmetry at play. Okay, that term is already there, lambda theta delta, right? So it's lambda plus lambda delta theta minus lambda theta delta. But then that's not all. You also sort of get another extra term with two deltas in it. So which is minus lambda delta delta. So that's the final answer. Okay. So this is how the product S alpha naught S theta acts on lambda. So this is S alpha naught S theta acting on lambda is this. So that's the final thing I want. So for now it's just some somewhat involved computation maybe, but the thing to note is that what we saw this morning was sort of the leading terms of this expression. So if you ignore for now the coefficients of delta, okay, so forget the terms which involve a delta, then it just looks like lambda plus lambda delta theta, right? You only have the first two terms, okay. And if you sort of look at, these were exactly the two terms that Raghavan wrote out. When you have lambda inner product with delta, so observe sort of as a remark to sync up with what you saw this morning, sort of remark. Taking an inner product with delta is the same as evaluating on K. Okay. So try proving this. It's just sort of our various dualities at work. K, remember, is an element of H. So what this is saying is, taking an inner product with delta, so K and delta are sort of duals with respect to this form. So this sort of says that what you saw this morning, the first two terms look like lambda plus lambda k theta. Okay? And so, as Raghavan pointed out, when you take that plane P where things with coefficient of lambda naught is 1, there this term lambda k turned out to be a 1. So on that plane, this formula reduces to lambda goes to lambda plus theta, modulo delta, of course. Right? Remember, there is also a further identification by this action of C, and things which differ by delta you think of as being the same. So if you sort of forget the delta part, this is exactly a translation. Lambda goes to lambda plus theta. Okay? But it sort of pays to also write it out in all its glory. Now you're thinking of it as really a linear operator acting on the full vector space H star, given by this, at this moment, somewhat unilluminating formula. But my goal is to sort of illuminate this just a little bit more. So here's this funny looking action of this product. But let's give this guy a name. Let's call this T theta, where T at least in our minds, should stand for translation, because at least on that plane P, we know that this operator acts by translation. I mean, once you identify modulo delta and so on. So once you, sort of restrict to a subspace and suitably identify things and do all that, you can convert this linear operator into something which is not linear, sort of more affine. It also does some translation. So, this acts somewhat like translation, but for now it is a linear operator on H star, okay. So, which is called T theta at this point. Okay. So, now, so yes, so I will now try and list a few properties of T theta. So, sort of here's maybe facts, or maybe let us call it proposition. So, various observations about T theta. So, the first question is this, what is the genesis of this somewhat strange looking formula? What does this look like? So, this term sort of in the middle is somehow key to the whole thing, which is why I sort of bracketed this guy, okay. So, it has this funny looking anti-symmetry, right. Anyway, so let's do the following. Let's consider, let's forget all the rest. Let's only look at the thing in the middle. Let's give that a name. So, let me call that tau theta. So, let tau theta just be the term in the middle. So, let this be the linear transformation which does the following to lambda delta theta minus lambda theta delta. Sort of like some kind of skew symmetric form. So, that's the linear. So, observe it is a linear transformation. So, this is now, well, not necessarily invertible. In fact, it's most certainly not invertible. It's more or less a rank 2 transformation at the most. Everything is being sent to some multiple of some linear combination of theta and delta. So, it's just some linear transformation on H star, okay. So, proposition, this is just definition, let. So, here is the proposition, this map T theta is just what you would get if you exponentiated this map, okay. So, I have a linear transformation from H star to H star. So, we know what it means to exponentiate a linear operator, right. It is just e power a is just identity plus a square over 2 factorial a cubed over 3 factorial and so on. So, it's a convergent series. You have to sum the series up, and the claim is if you do that starting with this sort of rank at most 2 operator, what you get is exactly that funny looking formula there, okay. So, let us check. All we need to do is just look at what is identity plus tau theta plus tau theta square over 2 factorial so on, but the first 2 terms are already there. So, observe the first term is identity acting on lambda. So, identity is right there, the linear term is already there, that is tau theta. So, we defined it. So, well, we need to somehow see how this what is left is the sum of all the remaining terms. So, these 2 terms already appear, and so we need to just worry about the remaining terms. So, let us compute tau theta square. So, let us apply tau theta twice. So, the first time you apply tau theta, you get lambda delta theta minus lambda theta delta. So, this is lambda delta theta so that is your new lambda, and now to this you must now act, okay. So, it's probably too confusing to keep all these terms the whole time. Let me just say some multiple of theta plus some multiple of delta, that is what tau theta of lambda becomes. I will worry about these multiples later on if I really need them, and then I need to take this with delta and multiply by theta minus I take the same thing, some multiple of theta, some multiple of delta, with theta and multiply by delta. Okay, so maybe we will just call these, I might need them. So let me call them A and B. It's called A theta plus B delta. Right, that's what you get when you apply it twice. It's fine. Okay, so now let's see, delta with itself, inner product is 0, delta with theta also a 0, right. So I don't need to worry about the first term, it's a 0, I don't need to care what the A's and the B's are. Now the second term, delta with theta is still a 0, so I don't need to worry about this. The only surviving term is theta with theta, which I know is 2. So my final answer is minus A 2A delta. And remember what was A now, let's go back and see what the A was. It was lambda delta. It's minus 2 lambda delta. Right, did I get it right? Okay, so I got the exponential of tau theta, the second order term turned out to be that. And so of course when I do tau theta square over 2 factorial, that's minus lambda delta delta. That's exactly the term I already have. So in fact this term that's there is just a second order term, the exponential. Which means that, well, I'm done if all the remaining terms vanish, right, which they do, because if now I have tau theta square, and if I figure out what I get when I apply it once more, tau theta to this would involve having to compute delta with theta and delta with delta. So observe that the remaining powers of tau theta just vanish identically. So observe tau theta greater than or equal to 3 is just identically 0. Okay, so we are done. So this strange looking formula is in fact nothing but the exponential of something somewhat less strange, I guess. So it's some kind of skew symmetric. I don't know, Shiva, is this something that would appear naturally in? So it's I mean, sort of in physics. I mean, if you are attempting to write it, using this notation, this is what it would be. Right? This is what physicists would write, for example, for this funny looking operator, because it's inner product with delta times theta minus some kind of skew symmetric thing. Okay, so that sort of already makes our life much simpler, because we now have a handle on what that operator does. So we observe now. So let me just try to reel off the remaining properties. So let's do the following. Since we know what t theta is, let's also do the same thing for any. So observe that tau theta now makes sense for, instead of theta, if I replace it by any other element of H star, the same thing makes sense, right? I can just put, instead of theta, I can define tau alpha of lambda by lambda delta alpha minus lambda alpha delta. That would still make sense for any element of in fact of H naught star. So this is, so if alpha is an element of H naught star, then let's do the following. Let's define the analogous operator tau alpha by the same formula. I'm sorry, what? The physics notation, is it? Let's see. So this would mean first inner product with delta. So you take lambda, inner product it with delta, and then you multiply it by theta. It's always a little backwards, I think. I mean, you should think of this as delta lambda theta, I think, in some sense. Yes. So if you define tau lambda of alpha, tau alpha of lambda by the same lambda delta alpha, minus lambda alpha delta, it makes sense for any element of H naught star, not just for theta. So you can sort of make this generalization and observe, if you define it that way, then what property do we have? And then let's also define its exponential. That now becomes an element of GL8 star, and that would be given by the same formula as we have here. You know, the first two terms would be the same, but the third term would be slightly different. So let's figure out what does this operator look like. What does T alpha when it acts on lambda? Because the first term is identity plus second term is just tau alpha, so it looks like lambda delta alpha minus lambda alpha delta. But what's the second term going to be? So when you exponentiate this, it's going to be slightly different. I mean, we have the calculation there, we just need to plug alpha in place of theta. So, right, exactly. So you get alpha alpha in place of 2. Okay. So no, I'm just taking any element of H naught star. No, at the moment the definition still makes sense, but I'm finally only going to apply it to that case. Exactly. So at the moment, so this is going to give me minus half alpha alpha. The half is, you know, from the 1 by 2 factorial, and for theta this number was 2, but if I pick any arbitrary element of H0 star, that won't be the case. Instead I will incur that norm term there, alpha alpha, and times lambda delta delta. Okay. So that's going to be, so this sort of so that's a precise formula for what tau alpha is, and you know, if you sort of look at CAD, so this is probably one of the most important formulas of chapter 6 of CADs. So in some sense this is obtained by seeing what happens to theta, which is a natural thing to consider somehow, and then observing that, you know, you could very well replace theta by any element alpha of H0 star and you would still be able to do similar things. So the formula now, you know, visibly incorporates the norm of that element.
I'm sorry, but why did you start with theta?
Why did I start with theta? It's not an easy question to answer. I think, so in some sense you want to understand S alpha naught. That's still, you know, probably the main objective. But, you know, alpha naught and theta are the two things which are related to each other, you know, directly, because their sum is delta, and delta is somehow this null root, you know, which is fixed by all elements of Weyl group. So because of that, several simplifications result. So this is the key relation. This is why you sort of want to pair these two things together, you know. And there I used the fact theta was 2. If alpha is an arbitrary element of H0 star, it won't be 2, it will just be some number which I called alpha alpha. So how did I get this? Exactly by following that computation on that far board. Is it the same? No, it's not going to be that. Okay, so what is the point of defining this general object? Well, you know, one sort of observes the following. So let's, you know, we've generalized it, and now let's study this for its own sake. If you look at alpha and beta, any two elements of H0 star, the claim is that T of alpha plus beta would just end up being the product of the two things, right? And why is this true?
There is no relation between T alpha and S alpha and S alpha.
No, I still haven't answered your question. That's probably my point 4 or 5. So yeah, bear with me for another. So why is this true? Exactly, it's defined after all as exponential of something, right? So all we need to do is look at what is exp of tau of alpha plus beta, right? And tau of alpha plus beta, so the key things to observe now are the thing to analyze really is what is tau of alpha plus beta. And the definition of tau is it's just that it's linear functional. If I change where do I have it? Tau alpha is here. So here I put alpha plus beta, here I put alpha plus beta, I will just add, right? It's linear, but more important, that's of course not enough. Clearly they commute. Right? So it's just linear in alpha and beta. So observe that the taus commute, and therefore when I take x, I will just get the relation on top, right? Because the this is just e power exponential of tau alpha plus beta is exponential of the sum, but these two things commute, so it's exponential of tau alpha times exponential of tau beta. So I know that this property is true for all alpha beta in H0 star.
So what's the composition of beta? Same.
Tau, right. Sorry. Of course, this by itself doesn't mean anything. So, okay, this is the first thing, and then I need to figure out what is composition. Correct. That's what I. Thank you. Right, that they commute. Okay, so let's see what do you get when you compose tau alpha with tau beta. So I think here's sort of where that physicist notation really makes life easier if one can handle it easily. So for example, tau beta would be okay, let me not really worry about this. So let's actually compute. So if you look at tau beta of lambda, so tau beta, so we'll just need to do one of the two computations. Tau alpha, tau beta of lambda would be, so this is tau alpha of, now it's like computing that second order product. So in fact, it's exactly the same computation that's on the last board, except now instead of that norm term, I will get an alpha beta term, that's it. So now it's just going to be minus 2, instead of minus 2, I will just get minus alpha beta, lambda delta. So this is just that quadratic computation. When you compose two taus, what happens to the answer? There we said what happens when you compose the same two taus, tau alpha square. But the computation is the same thing, tau alpha, tau beta is more or less the same. But instead of alpha alpha, I will get alpha beta. So clearly because of the symmetry of the form, it is the same as tau beta, tau alpha. Right. So okay, so they commuting exponential. So of course I get the property above, right? And of course, how does this relate to? So coming to Venkatesh's question, why did we get started on this thread? Because the tau theta, t theta, turned out to be related to it was an element of the affine Weyl group. And recall the observation which started out this whole thing is that if you take alpha to be theta, then in fact it's an element of the Weyl group. Right? And so this observation here, number 3, already produces several more elements of the Weyl group. Okay? We know that t theta belongs to the Weyl group, and this thing says if you look at t theta square, t theta times t theta, that's just the element t 2 theta, right? And every integer multiple of theta for the same reason would belong to the Weyl group. So automatically from property 3, you already conclude there are several more elements in the Weyl group. Okay. So that's it's already some use to this sort of more general point of view, but there's more. If you look at let's now take an element of the finite Weyl group. and let's now take any element alpha in H0 star, then look at W T alpha W inverse, turns out to be here's the next property that these operators possess. When you look at an element of the finite while group, you look at W T alpha W inverse, then it's just T W alpha. Okay. Again, a question of checking on the tau's before you apply the exponential. Okay. So let's check to see what happens when you apply this conjugation operation to a tau. For example, what is W tau alpha tau inverse? Okay, so it's a much simpler object, only the linear terms. So I first apply W inverse to lambda. So I get a W inverse lambda, W inverse lambda, and then I do the tau, and then I need to apply a W again. So when I do that, I get a W alpha, and there's nothing on the delta. So let me just write this down. So I sort of get the lambdas get replaced by W inverse lambda, and the alpha gets replaced by a W. But W delta is delta, so nothing happens to delta. Okay, is that fine? When I apply this conjugation to the tau, that's how it transforms. Now, is that the same as, what can we say about this form? So again, this exercise which Raghavan mentioned this morning, this form is in fact W invariant. Okay, that normalized. So it turns out this is exactly that normalized invariant form that Punitha talked about, and that's in fact a W invariant form. So I can push this W inverse from the first component to the second. Okay, I can do that also in the second term. So here's what I would get. It's lambda with W delta, which is the same as delta. So W alpha there, minus, can I have lambda W alpha delta. Right? And now I use the fact that W delta is the same as delta. Right? Delta is fixed, as we observed, by every element of the while group. So this fellow here is just delta, and so that's exactly the formula for tau W alpha. Right? It's lambda delta times W alpha minus lambda W alpha times delta. So that's just tau W alpha. Right? So the conjugation tau of W alpha is just the corresponding conjugate of tau alpha. So now we just apply exp. So by applying exp of tau W alpha is just the usual thing, e power W tau alpha W inverse. But when you have an exponential, you can pull out the conjugation from every one of the terms. So this is W exp of tau alpha W inverse, and that's what you want. Okay, so that also proves this next property, that how these T's behave under conjugation by the finite while group. So observe, I used the fact that it was a finite while group somewhere. Okay. So I needed the fact it was part of the finite while group because of course W alpha wouldn't be an element of H naught star otherwise. Because alpha is an H naught star, W alpha would also need to live in H naught star for this proposition to even make sense. And that's only true if W is an element of the finite while group. Okay, so this proposition gives us several more elements of the while group. Right? So always remember, this is sort of the primordial one. This is the one guy from which we are now bootstrapping. We are going to find several more elements from the while group, starting with this one fellow. So we have already managed to find all multiples of theta, the corresponding t's all belong to the while group. But now this conjugation property says, since t theta is there, so corollary to this conjugation property says, since t theta is there, then and of course remember, all elements of W naught are in W. So this implies, so observe, t theta is in W. Of course W is an element of W naught, which is in particular a subset of W. Therefore the conjugate is in W, and therefore t W theta is also in W. Right? So the fact that t theta is in W tells you that everything of the form W theta, t of W theta is also in W. Right? Now what do we know about the set of elements of the form W theta when W ranges of the while group?
Now we are in type AD.
Right. So I assumed for a start that my root system was one of the simply laced ones. It's all vectors of the root system, right? This was sort of one of the early assignment problems, that in any of these root systems, all roots of the same length are conjugate to each other under the while group. And W theta will run through all roots of the same length as theta. But then that's all roots of your root system, okay, if you are in types ADE. But of course, I just did this ADE assumption to sort of simplify my life. If you were to redo this whole thing in general, you could get exactly the same conclusions, except now you would say that W theta will only run over the long roots of your root system, right? Because remember, theta, as Raghavan mentioned this morning, is a long root of your root system, and therefore when you say t W theta is in there, you are only running over all the long roots of your root system. Okay, so therefore conclusion, this means that if you take t beta, it belongs to W for all beta which is a root. So this is a root of the finite root system which is long. Long roots just means all roots of whose norm is the same as theta. Think of it like that. Okay, so all root systems, if a root system has roots of two different lengths, long just means the one whose length is longer. And theta is always one such root. It's always a long root. And so you can characterize long roots as just all roots whose norm is equal to 2 or equal to that of theta. Okay, so we have now concluded the following fact, that so what are the various types of things that are there? T thetas are in W. In fact, more generally, everything of the form T of a long root is in W. And if I have two long roots alpha and beta, then T alpha, T beta is in W. Their product is in W, right? Therefore, T alpha plus beta is also in W. So in fact, further conclusions, so now use 3. So it's sort of further use 3 to conclude the following. Let M denote what Raghavan called this morning the long root lattice. This is the Z span of the while group orbit of theta. You can sort of see where this is coming from now. I need to start with theta. I need to look at all its while conjugates. And I know that will span that will give me the set of all long roots of my root system. Okay? And now I know for sure that T of all those betas are in W, and therefore so are T beta plus gamma, where beta and gamma both come from this set. Okay? And therefore the whole lattice generated by the long roots, T of every single one of them is in the while group. So let M denote this lattice. Then the final conclusion we have just made is that T gamma, so for all gamma in M, the corresponding element called, denoted T gamma is surely an element of the Weyl group. Okay. So, starting from theta, we have produced all these several elements. We first produced the Weyl group orbit of theta, and then the lattice generated by that Weyl group orbit. Okay. So, this is what we would usually call the long root lattice. In the cases of A, D and E, this is just what you would call the root lattice. It is the lattice which is generated by the set of all roots. Okay. And now, so therefore, we have now found two subgroups of this Weyl group W. Okay. One, the finite Weyl group. This is a subgroup. This is the one we started with. But now we have also manufactured this second subgroup consisting of all these T gammas. So, let us give that guy a name. Let us call it T, where T is just all these T gammas. Right. So, we have manufactured these several more elements, and we are going to claim that the Weyl group is nothing but the semi-direct product of these two things. Okay. So, this is the statement that Raghavan wrote out this morning. So, that's sort of the theorem or proposition. The affine Weyl group W is in fact the semi-direct product of these two subgroups, T or T of M, okay. Let us see. So, what are the parts of the proof that, let us see what are things we have already done sort of by way of these various intermediary lemmas. So, what all would we need to show? Firstly, that they have trivial intersection, that W0 normalizes T, right. So, that we have already shown. So, observe that was that proposition, right, that W T whatever it was, phi. So, W says that W naught normalizes T. So, that we have already said. So, proof, okay. So, observe already we know that W naught, okay. So, this is the thing, W T, W inverse, subset of T. That we have proved. The fact that they have trivial intersection you can sort of view it as as already having been proved this morning by Raghavan, because what Raghavan proved was, if you look at T theta in particular, but if you sort of I just erased the formula for the T alpha. So, we noticed how that T alpha, the fellow that we defined, acts. It has the same property more or less as T theta, that when you restrict it to that plane P that Raghavan defined, it is still that same translation. It does the following: it is lambda plus, so the first two terms when you look at the formula for T alpha was exactly like the formula for, it was the lambda delta alpha portion plus some stuff involving delta. But this was the key part that we used to think of these T's as translations. So, now when you put when you restrict to that plane with the lambda naught coefficient 1, on that plane these T alphas act by just a translation. They map lambda to lambda plus alpha, okay. But on that very same plane, the elements of W naught act as linear transformations, Okay. So, if you look at things as a form lambda naught plus some alpha, things here act linearly on that plane P that was defined this morning, whereas things here act as translations, as affine maps on that plane. Sort of again modulo the delta. So, all this is using all those identifications that we did this morning. So, essentially using that argument, it says when you have linear operators and translations, these two groups can't have anything except the identity in common, right, because the origin is moved by these fellows, whereas these fix the origin. Okay. So, essentially this is what has already been proved this morning by using that point of view as affine transformations. Okay, and then we need to show that every element of the affine Weyl group can be gotten from one or the other, but that we have already proved, right. Why did we prove that? How did we prove that? Because that was a starting point of this whole song and dance. S alpha naught was that extra fellow that we were trying to get hold of, and to get hold of that we sort of hit it with an S theta, and that gave us this sort of magic element T theta, right. So, S alpha naught is in the product, it is nothing but this times S theta. So, that extra element is surely in this product of these two things. Okay. So, in fact, we have shown all the things that you need. So, 3, observe, this we have already done. Okay. So, in fact, the Weyl group, the affine Weyl group is nothing but the semi-direct product of these two groups, these two subgroups. And now the question is, what do we know about the structure of these two subgroups? W naught, of course, is the finite Weyl group. So, let us assume we understand the finite Weyl groups. For example, for SL and C, we know this is nothing but Sn, right. So, there is some, we have some handle on what these finite Weyl groups look like. The question is, what is T? What kind of group is it? Firstly, is it abelian, non-abelian? Abelian, right? It consists of the elements are just T gammas. Their gamma comes from that certain lattice. So, it is certainly abelian. T gamma T of gamma 1 plus gamma 2 is T gamma 1 T gamma 2. But in fact, that formula T gamma, this thing here says it is just the lattice M. It is isomorphic to the lattice M. So, if you think of the group T, this is nothing but it is isomorphic to the additive group of the lattice. I mean, the exponential map is, the map whatever gamma going to T gamma sets up this isomorphism between these two things, right. So, in fact, the affine Weyl group is nothing but the semi-direct product of the finite Weyl group with this lattice. Okay, it is a semi-direct product with this very nicely behaved abelian group, free, finitely generated free abelian group. And in fact, that lattice also has this, it is intricately tied with the representation theory of W naught. It is not some abstract lattice, it is in fact the long root lattice, right. So, that is sort of the key point of this. Okay, and sort of the last remark, which I guess is a repetition of what Raghavan has already said this morning, you can, this is sort of the picture where you think of the affine Weyl group as acting by linear operators on H star, but by suitably restricting, by looking at that plane P and taking that identification by delta, you can now think of these as affine transformations. By affine transformation, we mean something which, it's either a linear operator or a translation. Okay? It doesn't fix the origin. So, that's also sort of the other origin of the word, the genesis of the word affine. Maybe the original context in which they were defined was where you thought of this group as really acting on that space H0 star, the same L dimensional space on which W0 acts. You take the same space and you make W act on it, but not by linear operators. You also include translations. You allow this group T to act by just translations by alpha. Okay. So, you could sort of also develop the theory in that way. That was classically how McDonald did it, for example. So, you can think of the Weyl group as, there is a representation of the affine Weyl group on an L dimensional space as affine transformations, okay, which is W0 and translations by alpha. Those are generated by those two things. And then you can define, a notion of an affine reflection. So, just like we defined our reflection groups, our reflections were sort of reflections in hyperplanes. So one thinks of a finite Weyl group as being generated by that picture that we had. Think of these as the hyperplanes. Reflections about the hyperplanes, they sort of generated the group S3, the finite Weyl group. Now instead, if you also allow translations, you can think of this, you can look at the following group. You look at these planes and you also look at translations of these planes. So for example, take this plane and sort of look at these guys. Okay, maybe I can get one more right, but that'll about. Okay, and I'm sure this is not right, but I'm sure it doesn't quite pass through the right things. Anyway, so you get the idea. So there's this. You imagine taking just the usual SL3 picture, but also allowing these planes to now sort of be all over the place. And now you can define something called an affine reflection. You think of a reflection of space, for example, about okay, here's the origin. You look at this plane. So things you still make sense of what a reflection means. So there's a mirror sitting there. You can still reflect about that. So there are several of these mirrors all over the place, and now you can say, okay, what do I get? What group do I get if I take a reflection about all these planes, not just the three things which pass through the origin? And the answer is that is exactly this affine Weyl group here. Okay? You can think of it also as a group generated by reflections about affine hyperplanes, not planes necessarily through the origin, but also things which are off. So it turns out that is an equivalent description of this affine Weyl group. But that T alpha, so sort of my last remark that I'll make, that formula for the T alpha, which I think was probably originally due to Katz, maybe even this way of thinking about it as linear operators was probably a very important discovery. And this funny looking formula that he had, especially for the T alpha, when we computed, we had there was this term which is quadratic in the norm. So there's lambda delta alpha minus lambda alpha delta. That was our sort of the linear term we started out with. And then the quadratic term in the exponential turned out to be minus half alpha alpha delta. Now it turns out that this particular term, sort of this quadratic term in the there is a lambda delta. Delta, yes. Right, so that's the formula we had, and this quadratic term that we have is sort of, at least Katz makes the remark that this quadratic term is really the origin of the connections between this whole representation theory of sort of affine Katz-Moody algebras and these very important objects in number theory called theta functions. So there are these objects that I will probably just mention in my subsequent lectures, but theta functions are, for example, in the naivest avatar, you can think of it as you have several, you have a lattice in the plane. So sort of this is the maybe simplest example. So you just have the square lattice in the plane, and you have just the usual inner product, the standard inner product on R2. And now, therefore, all lattice vectors have norms. For example, this is of norm 1, this is of norm 1, root, this is whatever norm squares, this is 2, and so on and so forth. So all vectors have this object alpha alpha. And so you sort of think of a generating function for the norms of vectors in this lattice. So for example, you sum over all lattice, where M is some lattice, and you say, okay, I sort of want to understand how many vectors are there of each norm. So you form a generating series like this, and you ask, what can I say about the properties of this series? So for example, this would tell you the power of q would be 1. The coefficient of q power 1 would tell you how many vectors there are of norm 1. The coefficient of q square will tell you how many vectors are of norm 2, and so on. And this is interesting if you sort of have other kinds of lattices. For example, something like this, and vectors have all kinds of funny norms in some sense. And so this whole business of studying, so such an object is called a theta function, suitably decorated. And instead of lattices, you also study often translates of lattices. You take this lattice, you sort of move it by something, and you ask, okay, what can I now say about the norms of those? And that's sort of a very classical part of number theory. Quite a bit of work long before affine algebras were invented, starting with Jacobi in, I don't know, the 1840s and so on. Sort of, there are several results about theta functions. In fact, the whole treatise by Jacobi on theta functions, for example. And it turned out that this little term there is, according to Katz at least, the reason why affine Kac-Moody algebras, and they have turned out to have a lot to do with theta functions. So this quadratic term, it looks exactly like that. And in fact, often the conventional normalization is this when you construct a theta function. So this is the reason why affine Kac-Moody and theta functions are often seen in the same sentence. That's sort of the moral of the story. Okay, perfect. We finish.